Professor in Mathematics at Chandigarh Group of Colleges, Landra. Today, we'll discuss about random variable. The contents of this talk will be the introduction about random variable. We'll discuss what is the random variable. Then the significance of the random variable, types of the random variable, and discrete random variable probability function throughout the session. Now, introduction. Random variable. Random, as the dictionary meaning suggests us, as the name suggests us, it is random. There is no fixed position for that. When you cannot predict the exactness, when it is just moving around. In business world also, if you look at the stock exchange, if you look at the body temperature, blood pressure, it is not fixed. It is wavering all the time. It is being changing. Such a situations cannot be predicted for a fixed value. There is a concern that we do need the term random variable. Yes, variability is widespread in the business world. To model variability probabilistically, we need the concept of a random variable. Now talking about that how this random variable is how it is behaving in certain situations. A random variable is a numerically valued variable which takes on different values with given probabilities. Some examples are the return on an investment in a 1-year period, the price of an equity, the number of customers entering a store, the sales volume of a store on a particular day, the turnover rate at your organization next year. These things are better assessed under the concept of random variable. What is the significance? To model variability probabilistically, we need the concept of a random variable. Secondly, for the theoretical distribution, these theoretical distribution will be like binomial distribution in probability, Poisson distribution, and the normal distribution. So all those theoretical distributions, during that process of calculating, we actually need the concept of random variable. Then comes sampling, which is quite famous in data science for large samples and small samples. Here also, we come across certain situations in which concept of random variable is very much needed. Now, types of random variable. First of all, I am taking here the discrete random variable. All those values that takes on countable number of possible values, for example, total number of roll of 2 dice, number of desktops sold, either it is none of that is sold for a particular day, or it is 1, 2 and many, customers count in a store, that is there is total empty store or big rush of customers are there. In all these situations, the numbers are not fractional. These numbers are not in terms of decimals. In such a situation, the discrete random variable is considered. In the second type, continuous random variable, one that takes on an uncountable number of possible values, for example, some interest rate that shows 3.25% or 6.125%, or the task completion time, that could be a non-negative value, any non-negative value, price of a stock, that is again a non-negative value. All such situations are better assessed under continuous random variable. So basic concept behind these two discussions was integers or rational numbers are discrete while real numbers are continuous. So in whatsoever situation we are, we'll first focus on the number of count. If it is pointing towards the integer or rational numbers, then it is the case of discrete random variable. If it is pointing towards the real numbers, then it is the case of continuous random variable. Now is probability distribution. Randomness of a random variable is described by probability distribution, how random it is behaving. Informally, the probability distribution specifies the probability or likelihood for a random variable to assume a particular value. Formally, let x be a random variable and small x be the possible value of x. So in the second point, it was totally theoretical touch of the concept. In the third point, it is the mathematical touch of the concept. Then we have two cases. These two cases are, one is discrete, another is continuous. The probability mass function of x specifies px, either it can be written as capital X is equal to x, even though we do write only this px, that goes without saying that it is under a particular value of capital X for all possible values of x. Continuous, in the case of continuous random variable, we will be coming across the probability density function of capital X is a function fx that is such that fx is h, which is lying between, that capital X is lying between x and x plus h for small positive h. So basic concept here, what is the bottom line of this concept, what we are discussing? The probability mass function specifies the actual probability and the probability density function specifies the probability rate. Both can be viewed as a measure of likelihood. Now, discrete distribution. A probability mass function must satisfy the following two requirements. One is the probability must lie between 0 and 1, which is the thumb rule of the probability, because probability can never be negative, probability can be equal to 0, equal to 1, but it cannot exceed more than 1. So that is the actual concept. And again, thumb rule of probability, that is sum of all the probabilities is equal to 1 for all x. So we are just between around the concept here, that we are following these two conditions of the probability, that it will lie between 0 and 1 and the sum of all the probabilities for a random variable will be equal to 1 only. We have taken an example here. Empirical data can be used to estimate the probability mass function. For this, let us consider that the number of TVs in a household are mentioned this way. These are the number of TVs and these are the number of households. In a particular city, you come across the statistical data about that how many people actually do not have TV at their home. These are 1218, and likewise those are having one, these are 32,379 and so on. So converting it into our mathematical way, wherever the number of TVs are there, these number of TVs will be named as capital X. This is the mathematical nomenclature I have done here. This number of TVs will be named as capital X, are so-called random variable. Then is the probability of each and every case. That probability will be the total number of values are sum of the all those number of households. This will be divided by the total number, this much amounts to the probability at x is equal to 0. So this way we calculate this to be 0.012. For x equal to 0, the probability 0.012 comes from this division. Other probabilities are estimated similarly. So the probability functions, a probability function maps, because function itself is a rule, it is a mapping. So the similar way, in the context of probability, what could be the definition of probability function that we are discussing here? That a probability function maps the possible value of x against their respective probabilities of occurrence, and it is mentioned as Px is a number from 0 to 1, and the area under a probability function is always equal to 1. So, it is an experiment in which a die has been rolled, the graph has been plotted. You can see here that these are the, this way the probability has been plotted, and this is the random variable. Sum at every point of time, that is 1 by 6. This is 1 by 6, this is 1 by 6, this is 1 by 6. At last it is 6 upon 6. When we do the sum of that, it is 6 upon 6, finally it is 1. That is why we are mentioning here the sum of all the probabilities, because 1 by 6 here is none other than, it is the probability. So sum of all the probabilities is equal to 1. If we see that in a tabular form, we come to this slide, that for x equal to 1, it was 1 upon 6, for 2 it was again 1 upon 6, and mind it, the way of writing the notation, here it is being written as probability x equal to 1. It is the probability for a random variable equal to 1, and this is the probability for a random variable equal to 2, and so on. Again, you can see here the sum is equal to 1. Next case is for the cumulative distribution function. We have seen in statistics as well that how the cumulative frequencies are calculated. These are being taken up back to back, and I show you in this example that how these have been calculated. If it is the random variable, then it is 1 upon 6 was the first probability, and you take on this 2 by 6, 3 by 6, 4 by 6, 5 by 6, and this is 6 by 6. This has been plotted in this graph, because you will be first calculating the probabilities, making a table of that, and then you will be able to draw a graph. After this, if we so far we are just doing the experiment for a random variable up to 6 only. With the help of simulation, we can create certain results like this. Flip coin virtually, and flip virtually coin 100 times, count the number of heads. Repeat this over and over again for a large number of times. Say it is 30,000 times. Then plot the 30,000 result. Manually it is not possible. Manually I could show only up to 6, or with a little more effort I will touch some higher level, but I cannot touch manually 30,000. For such situations, we take the help of computer simulation. So now, if you look at the result, you will get such a bell-shaped curve, such a normal curve, in which this is the number of heads in 100 coin tosses, and this is the count. You can see here the mean is 50, standard deviation is 5, and it is following the normal distribution curve where the 95% of the times we get between 40 to 60 heads. So, examples are, what is the probability that you roll a 3 or less? So, notation is for a random variable x, it is 3 or less, that is 1 upon 2. And what is the probability that you roll a 5 or higher? Then the probability will be written with this expression that P stands for the probability, x stands for the random variable, and 5 stands for the number for which we have been asked for. That is the value of the random variable at that very moment. So it is 1 minus all the previous ones. You will get here 1 upon 3. So there is one practice problem, that which of the following are probability functions. So let us calculate that. In first case we have fx is equal to 0.25 and the values for random variables, these are 9, 10, 11 and 12. Let's go. Function is 0.25 and the random variable values are being listed here 9, 10, 11, 12. Since it is a constant function, it won't change its value for any substitution for the value of x. So it is always 0.25. You can see here. And the summation of this expression is coming out to be 1. It is 1. Yes, it is a probability function because let me remind you two conditions, that sum of the probability should be equal to 1 and probability must lie between 0 to 1. So in present situation, although those two conditions are fulfilled. Next is we have this time not the constant function, but there is another function in which we have some x with us. The function is 3 minus x divided by 2. And the random variable is 1, 2, 3, 4. I have mentioned that random variable along this, that is 1, 2, 3, 4. Then substituted that value of random variable in the function at their respective places, calculated them, a very simple algebra is there, calculated them and we got to know that it is 1, 0.5, 0 and minus 0.5. As we discussed as the thumb rule in probability, that probabilities can never be negative. So in this case, we cannot consider it as probability function because this probability has come out to be negative. So though this sum is 1, you cannot have a negative probability, therefore it is not a probability function. One more example in this row, that is where we have the function x square plus x plus 1 divided by 25. So these are the random variables 1, 2, 3, 0, 1, 2, 3. This is the function where we have calculated all those values and this is there. When I calculated the sum of that, I am getting 24 divided by 25, which is not equal to 1, which breaks the rule that the sum of the probabilities must be equal to 1. And for this very reason, this will not be considered as probability function. So conclusion is that the variability is widespread in the business world. To model variability probabilistically, we need the concept of a random variable. Then is two types of random variables we discussed. One is discrete random variable and another one is continuous random variable. Randomness of a random variable is described by probability distribution, and for those probability distributions we discussed certain examples of that row. And a probability function that maps the possible values of x against their respective probabilities of occurrence px, and the area under the probability function is always 1. And we have seen in the previous examples that Wheresoever it was not equal to 1 or it was coming out to be negative, we declined it and we did not accept it to be a probability function. Thank you very much.